since you have analytical solutions, you have this complicated function for this deflection of your beam, why don't you use it? Why don't you integrate this thing with in a manipulator? Symbolical derivations, numerical simulations, animations, and optimization if needed, and everything in just using one screen, one piece of software. What should be the dimension of this arm? What should be the dimension of this arm? The rope length, how long should it be? And that's smelled like, optimization. The equations of motion, they do not exist. If it is a new system that you are investigating, nobody knows what should equations of motion be, and you need to derive them.
Hello, everyone. Today we are here with Professor Dmitry Sizov. Professor, thank you very much. It has been a pleasure, and thank you very much for agreeing and taking the time to be here.
Thank you very much, Lucas, for inviting me here. Yes, my name is Dmitry, and I work I'm with Mechanical and Aerospace Engineering Department in Nazarbayev University, Kazakhstan.
Great. And to start this amazing conversation I'm sure we're going to have, can you share a little bit about um, your current research aspects and where did you first became involved with Wolfram Language or Wolfram Mathematica?
All right, thank you for the question. So, my first experience with Mathematica, maybe it was 2013, I guess, 13 years ago, and the story is kind of really funny. So I've been always, passionate with the some medieval era, right? This moment, this time in the human history, and I just found a book which was something about siege engines, something like that, catapults, castles, this kind of thing. And okay, I'm reading about catapults, and there is this device called a trebuchet, right? So it's just a giant, how do I say, giant lever. You have this counterweight, right? You have this hinge. You have your projectile. You have a hinge, right? You have something like that, and as a mechanical engineer, a person who has mechanical engineering background, as a professor of classical mechanics, I just thought, whoa, that's interesting. That's an interesting device. So what we see here, there is this conversion of this potential energy of your counterweight into the kinetic energy of your projectile, right? And it turned out that the mechanics of this device is not trivial at all, right? So it has many degrees of freedom. It's governed by very complicated nonlinear differential equations of motion. And at that time, my knowledge, it was not enough to derive those equations properly. Maybe I needed a week or something. So I realized that I need some tool that will allow you to symbolically manipulate this kinetic and potential energy, all these Lagrangians and stuff. And it turned out that that's Mathematica, right? And I just I just found I remember there was a paper online how to do that thing for trebuchet in Mathematica. Okay, I opened Mathematica, I just retyped this code, pretty naive code, should I say, and it worked. And it saved me a week. It saved me a week of pen and paper work of all this non-trivial algebra and stuff. And yeah, I was amazed. I was amazed, and I'm still amazed. So this possibility of symbolically doing many, many complicated things, simplifying expressions, solving equations, that is just truly awesome. That was my first experience with Mathematica. And the thing is that currently I'm doing pretty much the same thing. So now I'm studying space systems, right? So classical mechanics applied to space systems, for example, systems for space junk removal or low Earth orbit satellites and stuff. And the problem there is that the equations of motion, they do not exist. If it is a new system that you are investigating, nobody knows what should equations of motion be, and you need to derive them. Again, exactly as for this trebuchet device, right? You need to derive everything. And how do I do that? Of course, I use Mathematica. And there is another thing about this trebuchet device. So after I investigated all the thing, I decided, okay, I would like to make a presentation. I would like to show people, wow, look at this. It is a wonderful medieval device. It's such a clever, such a genius device which transfers the energy and everything. Look how effective this is, how impressive it is. And I realized, okay, I need some animations now. I need some animations, and how do I do them? Since my mathematical model is in Wolfram Mathematica, okay, I did my animations in Wolfram Mathematica without changing my software, right? I did that. All right. So, and again, before I delivered this presentation, I thought, okay, maybe, uh, and what should be the dimension of this arm? What should be the dimension of this arm? The rope length, how long should it be? And that smelled like, optimization. And I decided, okay, I'm running this optimization on my mathematical model to understand what set of parameters maximizes the range of this device, the projectile range. And again, I did that in Mathematica, right? And yeah, I keep doing that, but now in this actual research, right? Symbolical derivations, numerical simulations, animations, and optimization if needed, and everything in just using one screen, one piece of software.
That's amazing, Dmitry, and that's amazing to see how you're excited to talk about this because it's not just only a tool for you. It's like almost a software that expands your way of thinking and how to approach problems. And that's gonna be
Absolutely.
exactly the next question I was gonna ask. How would you say, like in general terms, that Wolfram language or Wolfram Mathematica has influenced or shaped the way you approach scientific problems?
That's a very interesting question, not an easy one. I should say that now I'm not thinking procedurally. Now I'm thinking functionally, because Wolfram Mathematica is, first of all, it's a functional language, right? And that transition. To be honest, it's not easy for my students now. It wasn't easy for me back then, right? So if you write something and you're not supposed to use loops, you can, but it's not the Mathematica way, right? You need to use this high-level function like map thread, and stuff. And in the beginning, that's really non-intuitive. So how can I code without loops, right? So how can I code without I, J, and all this stuff? Okay, how can I code without procedures, without this if, for, when, then statements? And it turns out that you can. Turns out that you can, and I love this approach. I love this approach, and that's really kind of. I really learned how to write these functions. Yeah, you do not write the whole script where everything is a mess, right? As sometimes I see you just split your problem into a teeny tiny sub problems. For each sub problem you write a function, and then you just write this composition of functions. In Mathematica there is this very nice, my favorite function, composition. You just make this chain, and that's it, right? You can test every separate function, no problem. Then you join, and everything works like a charm. So that's really shaped my thinking this way.
I see. It's pretty amazing too that you mentioned that you changed the way of thinking, like in terms of computationally. And it's pretty amazing that sometimes, as you mentioned, like you can do animations. It's like doing what it's called like an experimental computation. Or you can experimentally verify, like as you mentioned in the first example, like the length of the rope, the weight. You can play around with this, and this helps you understand better the problem. So it's pretty amazing.
Absolutely, and faster. You just write a simple manipulator with 5 sliders. Just move, no, 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 like that. Should it be this way? Okay, maybe it should. Okay, oh, there is a mistake, and you just visually just track this thing down. Very, very. The manipulate function is just it's another of my favorites. Yeah, I really like
Yes.
it.
And it gives you like this pedagogical touch because you can show someone that let's forget about the code, just look at the animation. I'm going to explain you about what that problem is. Um, and talking about that, I understand that Wolfram language or Mathematica have plays an important role in your teaching, right? You have been doing a lot of courses that you use Wolfram Mathematica in your lectures. Am I right?
Yeah, absolutely. So I'm so lucky because my university has Mathematica. We have a license, and that is truly awesome that I can really introduce Mathematica in my teaching. So I inherited some courses when I first came there, and fortunately they were taught using Mathematica before me. And after I came, I took it over first, and then I introduced a couple of my courses, spaceflight dynamics, for example, and every lecture that I deliver is accompanied by a Wolfram Mathematica presentation. Every lecture, at least every STEM lecture. Yes.
And how
And in
do
this presentation, um, okay, so just imagine an ordinary lecture, right? So in this presentation, in your lecture presentation, you're supposed to show some theoretical material, right? So since it's a STEM course, you need to derive something, right? To just show the students that indeed that works, right? You need to perform some numerical simulations or computations, and of course, you need to visualize that, right? And most probably you want to animate that just again as you mentioned to be able to play around with some parameters very fast, right? To show the influence of this parameter, to show the influence of altitude, show the influence of mass or anything like that. And what is cool about that, that you can do all these things together without quitting Mathematica. So all my lectures, they are Mathematica notebooks, actually, Wolfram presenter tools notebooks, right? And sometimes I like to play tricks on my students. So just imagine there is this first lecture on engineering mathematics, right? And the students, they enter the room and they already see my presentation first slide. Okay, Dmitry Sizov, Nazarbayev University, and everything, and everything looks normal for a student, right? And then I start lecturing. Okay, guys, so here is your textbook, here is your schedule, here is your exam overview, something like that. And then I say, okay, so now, guys, we need to learn some mathematics. And you know what? We're gonna not gonna use pen and paper. Okay, maybe not entirely pen and paper. We're gonna be coding, and right away after I mentioned that, I just take my slide and I type 2 plus 2 and I evaluate, and 2 plus 2 is 4. And not every students, but many of them, they're really surprised because they expect some static slide that professor just teaching a usual way. It's a PDF, right? But it's not. And that's really funny trick. And after that, many people understand that yes, this guy is gonna teach us some coding.
That's very powerful, and I'm sure that the students get impressed by that because, as you mentioned, they expect some static slides or PDF. And um, talking about that, would you be able to share a specific example of some manipulation or some simulations that you do on your teaching?
I think yes. So, can I share my screen now?
Absolutely, yes.
As you can see, as I said, that's just an ordinary lecture on spaceflight dynamics. As you can see, week 6. So I delivered this lecture maybe 2 weeks ago. So as you can see, the Department of Mechanical Aerospace Engineering, School of Engineering and Digital Sciences, Nazarbayev University. So I'm showing the topic non-impulsive maneuvers, right? So what is non-impulsive maneuver? If your spacecraft is in orbit and you want to change your orbit parameters to, I don't know, increase your orbit or decrease or something like that, you need to burn fuel. Yeah, you need to fire your engines. And here we discuss the difference between impulsive and non-impulsive maneuvers because we covered this impulsive first. And then I derived some equations of motion. So as you can see, we have some equations without any engine. Now I introduced this engine force, basically just Newton's second law, right? And then, as you can see, everything is from our textbook, right? But here I provide a derivation in Mathematica. So as you can see, I just create some sort of a position vector, symbolical object, functions of t. I calculate the magnitude. I differentiate that symbolically, just basically adding these primes. So I create this dot function of mine, right? So I also created a double dot function to calculate accelerations, and there you go. ago. So we basically have these equations from the textbook, but now they are in Mathematica, they are symbolical. So it's not only I'm deriving that, I'm also kind of demonstrating the ability. It's really important for the students to know, even if they don't understand entirely, maybe sometimes they do not understand that what exactly I'm doing, what this thread function is doing, right? But at least they will know that this thing is possible, right? They will ask me, they will uh, Google this function, no problem. So I have derived the equations. And now let me, so I'm showing the whole system that we're gonna solve numerically, and we jump into a numerical example, right? And in this numerical example, as you can see, we need to jump from some orbit to another orbit. We need to perform burns, and I'd like to. So when I was preparing this, I thought, okay, so I need to animate these burns, right? I need to show the students how the orbit changes in real time, and it looks like it can be it is possible to do that in Mathematica. But to do this, let me show you. I needed to write, a couple of functions just to make this thing possible, right? To visualize everything. So I need to calculate the angular momentum, the velocity, right? The eccentricity of my orbit, many spaceflight dynamic things, pretty trivial things, right? But I needed these code to make my animations work. So let me finally jump to my animations. So for example, if we burning our engine at periapsis, the closest point to the Earth, we're rising our opposite point, the rising apoapsis. And after we numerically solve this system, the actual animation, it looks kind of like that. So look at this. We are originally in something looking like a circular orbit around this blue marble, around the Earth, right? Here is our periapsis, here is apoapsis. And now we start burning. As you can see, I use manipulate here. We start burning, we're moving in the orbit. And as you can see, our apoapsis gets up like that. So after we finish the burn, we're not in the old orbit anymore. We are on this transfer orbit. And then I simulate the another stage, which is called coasting. So we just keep calm and coast like that. We coast to the apoapsis like this, and as you can see, everything changes here. So everything is being computed. So we can discuss. Okay, look, guys, this thing is static. This thing is changing, right? Very, very convenient. And the last but not least, we perform another burn because we would like to uh, jump to this high, large orbit. We burn at the apoapsis, whereas our periapsis, burning fuel, changing our speed, increasing our orbit, and we circularized. And that is how it looks like if you have an engine, a pretty powerful engine, high thrust. And after we discuss all that, I'm showing another thing to my students. Okay, guys, and what if you have an engine which has a pretty low thrust? How would this burn look like, right? And it turns out that this burn just is splendid. Look at this. So the spacecraft is spiraling, right? Yeah, so instead of just having a very small arc with you have high thrust, you have something looking like that. And even to me, it's pretty impressive. So that was my typical lecture. As you can see, after we discuss all that, I just make some conclusions here. And I thank my students. And I just mentioned what textbooks covered. And sometimes I recommend things to try to solve this problem. And as you can see here, there's I just recommend my students try to understand the code that I used for the interactive demos. Yeah,
Wow.
something like that.
This is pretty amazing because not only you show them the animations are with the manipulative, and but you also show them how to derive these equations using Wolfram language, the symbolic computation embedded. So this is a very computational way of understanding something. So it's pretty amazing. And thank you very much for sharing that. I'm sure your students learn a lot from that.
I hope so. Yeah, my pleasure.
Great. And besides your lectures, I'm aware that you developed some packages in the past, like regarding many different applications. So can you tell us a little bit about that? I mean, what kinds of packages you worked on and what was the motivation to create those?
All right. So there were and still are two main reasons when I started writing packages is my research and my teaching. Right. So starting from teaching again, I'm just thinking. So sometimes I need just to, um, I don't know, to avoid complex coding, just to give my students a tool to use, right? And sometimes it's much better to write this tool by yourself, right? Because sometimes students they do not have time, right, to cover all those coding programs, uh, coding aspects. You just write a teeny tiny module and you say, okay, guys, you play around with that. So your project is going to be using that. So you just use my module, feel free to use it. And at the end of the day, your task is to solve the problem and to explain how did you solve it and how did you use this module or that module. And that is how, for example, this BIM solver package was written, right? So at the time, I was teaching some structural mechanics, beam banding and stuff. And I decided, okay, so this beam banding, you can compute this manually. There are other software, pretty brilliant pieces of software that allow you to simulate this particular beam. But what is really amazing that you can solve the equation of the beam analytically. And at that very moment, when I just realized that, I said, okay, I'm solving that in Mathematica. And so I needed a module in which you can specify, okay, how long your BIM is, where your supports are, what are the loadings, and you just see your deformation, and not only as a plot, as a graph, bending moment, deformations, and stuff are pretty ordinary things for a civil engineer, but you can go further. So, for example, since you have analytical solutions, you have this complicated function for this deflection of your beam. Why don't you use it? Why don't you integrate this thing with a manipulator? For example, you can have a force which can move, right? So, since you have this analytical solution, depending on where your force is, you can totally write and manipulate function and to show, look, guys, so here is this, I don't know, here is this car, going along this bridge, something like that. And look, the shape of the bridge is changing. And since it's analytical, it's already kind of pre-computed, it's really fast. So I just move this manipulator, and without any delay, my beam changed shape, and that's really amazing. Yeah, I'm still amazed by that. It is really a really nice way of visualizing that, and it didn't take long for me to write this. And yeah, that's just one of many examples that I used in my teaching. And turning to my research, that's another story. So here, when it comes to research, you need to be, you need to be competitive. You need to be extra efficient, right? And you absolutely want to write modules in order to not repeat some complicated code which you can easily forget, right? Because, for example, I wrote a module which computes, aerodynamic coefficients of satellites in rarefied atmosphere, and oh my God, that was not easy, right? It took a month at least to write to debug everything properly, and now, to be honest, I cannot even remember, 80% of the functions, right? How they work. I have no idea. Yeah, I knew before, but I forgot. But my module is still with me, right? And yeah, I'm still using that. It's a really nice module. And I have many modules, for example, two modules that facilitate my work with, some fancy kinematics concepts as Euler angles, Euler matrices when it comes to 3D rotational mechanics. Again, those matrices, they are even for me, I understand them, but every time you need to, okay, so what is my first coordinate set? What is my second coordinate set? Okay, how do I write this rotation matrix? You need to concentrate. But if you have those models which are pre-written by you and they are tailored to your specific task, oh, that's amazing.
Yes, I mean it's amazing how you use Wolfram language not only in terms of teaching but on research, but also on this maybe lecture motivated or research motivated packages. Let's say this thing does not exist, but I can create this using what I know about the problem and what I know about Wolfram language. So this is pretty amazing. And something I would like to ask you just for the sake of curiosity, I have seen a lot of people that uses Wolfram language or Mathematica not only in their jobs but in their life, like in their hobbies, for example. For example, we have some examples on food science that you use Wolfram language to know, for example, the heat distribution when you're going to boil an egg. So I find this
Mm.
pretty fascinating, and I have seen other kinds of example like let's map the wireless signal throughout my house using Wolfram language. I don't know. Have you ever tried those funny examples like trying to solve or just for fun to do something like this?
Interesting question. Yeah, I think I did, but it was mostly inspired by my son, right? So maybe it was a year ago. So I don't know. So let me tell you first this story about the year ago. So he came to me and he asked, "Okay, so I've seen this game somewhere, but now I do not know where this game is. This guy has left the city. Okay, so could you please write to me some sort of a random number generator, which looks like a disk. You have the sectors, each sector in different color. And since it is already 9, he understands something about probability. He told me, that the probability of this number should be 1%, the probability of that number should be 10%, and the probability of that number should be something else. And I wrote it in Mathematica. I said, okay, so here is your disk. Okay, here are those sectors. Then now they have different colors. And he said, okay, what about the probability? I say, okay, so there is a function to generate random numbers if you set this probability, right? So we did it. We did it together in less than an hour.
Wow.
So that's just the one of the examples that I can remember, can recall.
And how old was he at the time?
He was 9, so now he's 10. Yeah, so he was 9. Yeah, but yeah, so he
He
knew
was not.
somehow he knew something about probability. And to be honest, that was a teeny tiny pain in the neck for me to implement this probability. But
That's what I'm
but
gonna
we did
ask.
it.
Like, he was 9 and talking about probabilities,
Somehow, yes. I don't
and
know.
why did
You,
he
you,
need
you
like?
ask him. I have no idea. I have no idea, but he had very strict requirements. All right, so I need this
Wow.
probability, I need that probability, and I'm not even telling about color. So it should be this color, that should be shit color, without any exceptions or whatever.
This is this is amazing. I always like to see these kinds of fun projects using Mathematica. For example, I have a colleague that I interviewed a couple of weeks ago, and he likes to play Minecraft.
All right.
He likes to play Minecraft, and he discovered that he can map out, I mean, the entire map of Minecraft was available in a file. And then he like used Mathematica to uncompress and so to speak open the 100% map of Minecraft, and he could see like different levels deep down on the ground, and he could do a lot of cool stuff with that just for fun, you know. And I really like this kind of examples because it's a tool that not only is it can expand your way of thinking and how you can see about the world. So, and I see that you're like a very an eager user of Wolfram language and Mathematica. And
Yeah,
something
absolutely. Absolutely. And there is another example. So that is really funny. There was a party and we wanted to play Twister, this game that yeah, yeah.
yeah,
And we didn't have this randomizer, right? So there is this cardboard thing with this arrow and you turn it, right? Right hand green, left okay, so yeah, left leg blue, you got my point, right? And I say, okay, guys, I'm ready. Give me 10 minutes. I will write you this thing in Mathematica. And I did it. Again, it was about
wow,
random numbers. Yeah, that's a funny coincidence, but that's a true story. True story.
that's amazing. I mean, I really like that kind of stories. Like Give me 10 minutes and I will solve this problem using Mathematica. This is
Yeah, because
amazing.
it's really fast. Because you cannot beat Mathematica if it is about a writing a prototype very fast. Because of those high level functions, it's so easy, right? Maybe sometimes you need to polish it. Maybe you need to compile some things. Maybe you need to do something extra. But your prototype, you'll get it very fast, and that is awesome.
And pointless to say, but I can see, and we discussed this, how Mathematica and Wolfram Language has shaped the way you think about a lot of things, like even from lectures to research and to real problems that you have at your house. So my final question to you is a little bit different. If Wolfram Language had not been part of your journey, imagine that you never had that first encounter with Mathematica. How would you think that your career or even the way you think would have been different?
Well, that's a tough one. That's a tough one. Really, really hard to imagine, to be honest, because this language is with me, has been with me, for almost 15 years, and I do use it every day, so I cannot even imagine. So definitely, so if I think about my lectures would be static slides and more chalk and blackboard. Definitely no animations. Maybe yeah. So I could be passionate. I can derive something, but without those animations, just you cannot reach. So the no, no, that wouldn't work. That wouldn't work. And speaking about my research, definitely that wouldn't be possible because the systems, the new space systems I mostly work with, they require some tool that allows you to derive equations symbolically to make your process more robust, to make it faster, to be competitive, right? So you spend weeks on doing that, you're not competitive. So, sorry, but I cannot imagine my life without it. Yeah, so and yeah,
Great. I mean, I can see that maybe you had like you can give lectures, yeah, fine, but you couldn't reach that level of excitement that you
absolutely.
show here. Like it's pretty amazing. Like I can see, I can visualize you giving a lecture and being excited about your own lecture because it's really nice to have this manipulate and derivation of equations, and it's pretty amazing. So
Thank
with
you.
that, I would like to thank you very much for this interview, Professor Dmitry, and it was a pleasure, and I learned a lot from you. Thank you very much for taking your time to be here, and thank you very much for being so eager user of Mathematica and to share a little bit about that with us.
Of course, it was my pleasure. Thank you very much for inviting me.